So, chapter 4 is more force analysis. Chapter 3 was force analysis as well, but that was talking about sort of standard forms of forcing function. Chapter 4 is where we talk about Fourier analysis. Okay. So I'll give a brief introduction, and we'll talk about Fourier series, which you've covered before in maths. You've looked at the maths behind it, and this is how we apply it to vibrational systems. And then I'll talk briefly about Fourier transforms. Okay. In previous versions of this course, we dived into the maths behind Fourier transforms, but it's not really applicable. It was getting a bit abstract, so I've decided to reduce that the maths content out of that. But it's still important for you to understand what a Fourier transform does, and how it's applied to oscillations systems. So in terms of an introduction, chapter 3, we looked at specific non-periodic and periodic oscillations. Okay, there's non-periodic ones with a step force, a ramp function, and a decaying exponential, and the periodic one that we looked at was the sinusoid. Okay, so it's the most basic form of a periodic function. But what about other functions? Okay, they can be very complicated, and Fourier analysis allows for you to be able to deal with those complicated functions. Fourier series, which we'll look at first, will allow us to deal with periodic but non-sinusoidal problems. Okay, and Fourier transforms allow us to deal with actually non-periodic forcing functions and stuff. So with Fourier series, if a forcing function is periodic, so that it repeats over and over again at regular intervals, okay, then the function can be expressed as a Fourier series. Okay. And that Fourier series is a series of sines and cosines. So it's essentially a trigonometric problem. And so if we've got a function of period 2 pi, okay, so every 2 pi seconds it repeats itself, okay, then you can represent it using this equation. And so what you've got here is a constant force, a constant term. So if the averaged value of your periodic function is not 0, then you'll have a term out here. Okay, and then you've got a sum from n equals 1 to infinity of these sines and cosines, and obviously they will have certain amplitudes. Okay, an and bn. And obviously, depending on the function, you may have you may have just cosine terms, or you may have just sine terms, or you may have a mix of the two. Depends on the form of the function. And to work out what those coefficients are, an and bn, okay, this is again for a period of 2 pi, so it's a specific period. You've got these two terms, okay, and so what you do is you take your function, for which you know the equation of, okay, and you plug it into this equation between minus pi and pi. You take the derivative of that, you take the integral of that, okay, so the function times by cosine. Okay, and then obviously you can work out what an and bn are. So for different values of n, okay, n equals 0 through to infinity, and here with bn it's 1 to infinity. The reason there's a 0 here is obviously there is that constant term, and you can work it out based upon this term. Okay. So as a quick example, just a brief overview. Like I said, you have done it before. And I'm not going to ask you to get the Fourier transform in any assessment that you have, okay? Because it's not what I'm assessing. You should have been already assessed in this. But as a brief overview to just show you, let's assume that our forcing function is a square wave, okay? We've got a period of 2 pi. It's quite clear that this repeats itself after every 2 pi seconds, okay? And for between 0 and pi, we've got a value of 1, and between pi and 2 pi, we've got a value of 0. Okay, and if you describe this wave analytically, you can say that the forcing function is 1 between 0 and pi, and is 0 between pi and 2 pi, and t plus 2 pi, okay, is equal to f of t, because if you take a point here and you add 2 pi to it, you get the same value. Okay, here add 2 pi, I get over here, I get the same value, and so on. Okay, so the thing repeats itself every 2 pi seconds. Very, very simple forcing function. Now to calculate the coefficients, so an first off, we plug our equation. Here's our equation for an. Okay, it's pointless me evaluating from minus pi to 0 because we know straight away from the picture that between minus pi and 0 the value is 0. So the integral of that bit is going to be 0. So I'm integrating between 0 and pi. Okay, f of t, my function, we know is 1. Okay, between those points there, times by cosine of nt. Well, the integral of cosine is sine. Okay, and obviously because I've got an n here, I've got to have an n on the bottom. Sine of nt upon n times by 1 upon pi between 0 and pi is my integral. Well, if I plug in pi into here, into t, I get sine of n pi. Well, what's sine of 0? Sorry, what's sine of pi? 0. Okay, sine of 2 pi, 0. Sine of 3 pi, 0. And so on. So no matter what value of n is, this term is always going to be 0. And obviously sine of 0, because if I stick 0 in, obviously that also equals 0. So I've got 1 upon pi times by 0 minus 0, which must therefore be 0. Okay, so the an terms are 0. As long as n doesn't equal 0, an is 0. There's no cosine terms in my solution. If I go back to the solution, an times by cosine, okay, if an is 0, then therefore there's no cosine terms in that solution. So if we look at Bn, similar equation, sorry, before we look at Bn, that's the constant term, okay? If you remember back on this page, if n is 0, cosine of 0 is 1, so we just have the function between minus pi and pi times by the function. Again, we know that between minus pi and 0 is 0, but if I work out a0, we get a value of 1. Now, that's the constant term, but if you look at the equation, you can see it's a0 upon 2. So in fact, this constant term is a half. And that makes sense, because if you look at the square wave, okay, it's quite clear that you've got equal intervals of value 1 and value 0. So therefore, the average term must therefore be half. Okay. Now, it won't always be half. It depends on what your function is. But obviously, in this case, because it's spending an equal amount of time at 1 and an equal amount of time at 0, therefore the average must be 1/2, which is where that a0 upon 2 comes from. Okay, so the constant term is a0 upon 2, which is 1/2, from which examining the wave is clearly true as the square wave takes on values of 1 and 0 over equal length intervals. Now for the Bn terms, similar equation, except for this time we've got sine in here. Okay, so you integrate between 0 and pi, 1, which is the value between 0 and pi, sine of nt dt. Okay, the integral of sine is minus cosine. Okay, nt upon n between 0 and pi. Now, that's cosine of 0 we know is 1, so obviously this has got a value of 1 upon n. Okay, and we've got cosine n pi upon n here, and so you end up with this equation. Now, depending on the value of n, you've got different values of cosine n pi. It's quite clear that if you've got an even value for n, okay, so 2 pi, 4 pi, 6 pi, and so on, cosine, or 0 pi even, cosine is plus 1. Yeah? For sine of 2 pi over one period is going to be back at plus 1. Okay? So if that's the case, we go back to the equation. Okay, if this is plus 1, okay, for n, if n is even, then you have 1 minus 1, which is 0. So Bn must therefore be 0 for any even value of n. But if you've got an odd value for n, so 1, 3, 5, and so on, we know that cosine of 1 pi and cosine of 3 pi is actually minus 1. And so you have Bn is 1 upon n pi times 1 minus 1, 1 plus 1, so you end up with 2 upon n pi. And that's for even values of n. And so it's quite clear that our first term, where n is 1, we have 2 upon pi. Our third term, we have 2 upon 3 pi. Our fifth term, we have 2 upon 5 pi. But like I said, the even values, you have 0. So we only consider those even values. sorry, for the we only consider the odd values. So the required Fourier series is, there's our constant term, we have 2 upon pi, and then we have sine of t, okay, because obviously it's just the sine terms, there's no an term, so it's just the sine terms, 1/3 sine of 3t plus 1/5 sine of 5t and 1/7 sine of 7t, and so on, okay. And as you add more terms, it gets more and more accurate to what your original function was. And so here's the first 7 terms. You can see this is quite clearly, this dotted line here is quite clearly just the sine of t. Then you've obviously got sine of, you add that to another sine term, you get slightly better, and so on and so on and so on. And this line here, the solid line, is those 7 terms added together. And like I said, if you add more and more terms, it gets more and more accurate. You get more and more closer to my square function, but you will end up with an overshoot at these points. At any discontinuity in your function, you're going to end up with an overshoot. And that's just a consequence of Fourier series. It's called Gibbs phenomenon, and it will be no greater than 9% of the value that you wanted. Now, unfortunately, I have got a little MATLAB script that will show you that, but this MATLAB's not on this machine, so I'll have to show you that next week. So that was for a period of 2 pi. Okay. What about if we extend that period to t? Okay, instead of 2 pi. Then you've got this equation, okay, which applies. And so it's slightly more complicated, but obviously it's quite clear that if you stuck 2 pi in here, then that would cancel out with nt, which is what we had before. Okay, so this is a general period. This is the form that's on the equation sheet. And your an terms, again, you've got in terms of t as opposed to 2 pi. So again, it's quite clear that if you stuck 2 pi in here, you'd have 1 over upon pi, which is what we had before. And again, t by 2, obviously you stick 2 pi in here, you get minus pi and pi. Okay, so again, it's exactly what we had before. It's just this is in terms of general period t as opposed to 2 pi. Now, like I said, I'm not going to ask you to come up with the Fourier series for a particular function in the exam. You may, when you're looking, when we're going through past papers and stuff, you may see I have done so, but rest assured I will not ask you to do that, okay? It's not part of, like I said, not part of this course. In previous years, I focused quite a lot on the maths behind Fourier series. You've done it all before. I'm not going to assess you on that. But like I said, this is on the equation sheet if you need it. Now, obviously the application of this is applying it to a vibrational problem, okay? And so the advantage of that is we can deal with any periodic forcing function. So like I said, up to now, f of t has been a step force or a ramp force or a sinusoid. Well, now we can actually apply a periodic function, okay, where f of t is this Fourier series, which is a series of sines and cosines plus a constant term if there is one. So f of t is a non-sinusoidal periodic function, okay, then Fourier series may be used to obtain the steady state solution. It's actually very straightforward, because what you do is you take one of those terms, okay, take one of those terms from that sum, and you solve for x for that specific term, and you do it again for the other terms, and again for the other terms, and so on, until you get a whole series of x of n's, okay, and you just add them together to get your solution, okay? So the Fourier series is this, essentially. From n is 1 to n, you have a certain number of terms, okay? And each of those terms individually are called f of n, okay? So when n is 1, well, I've got f of 1, t. And obviously for that specific term, there's going to be a specific solution, x of n. Okay, and for f of 2, then I'm going to have a specific solution, x of 2. And so on and so forth until you get a load of x of n's, and you add them all up together to get your solution. Now that sounds onerous. It sounds like you're going to be repeating the same thing over and over again. But what you can actually do is you can solve it in terms of n. Okay, you don't have to solve it in terms of 1 or 2 or 3, whatever n value is. You can solve it in terms of n. So you actually only have to do it once, and you have to use the sum term here to solve it. And so like I said, where x of n is the response to the forcing function f of n. So it's a 3-step process. Like I said, step 1 you're unlikely to need, certainly for this module. okay, obtain the Fourier series for the forcing function. Step 2 is to solve the differential equation for the response x of n, okay, corresponding to the nth harmonic. So we're not being specific about n. We're just saying, okay, well, there's going to be an n term somewhere in there, and we need to solve for that nth harmonic, okay, in the Fourier series. Response x0 is a constant term, if there is any, okay, in the Fourier series, and may have to be obtained separately. And then you superpose those solutions, basically you're adding them together. You're adding them on top of each other to give the overall steady state motion, okay. So we have our constant term plus a sum between n as 1 and big N of x of n time, which is a function of time. And that gives you your complete solution, x of t. So, let's look at an example. The problem is to find the steady state response, x of t, of a mass spring system modelled by this, where f of t is a periodic square wave function. Okay? Our period, quite clearly, is 2t0. Okay? And the average value, what's the average value for this particular function, if this is 0? Average value? 0, okay? Exactly. It spends equal intervals at plus f0 and minus f0. So if you add up the things and divide it by 2, you end up getting 0. So there's no constant term in this particular example. Now we can describe analytically. I didn't describe it analytically, but obviously that can be described analytically. And to talk about the f of t as a period of 2t0, okay, so that omega is pi upon t0. Since it's an odd function, now you should know about odd and even functions. An odd function is a function that essentially if you draw it, you can rotate it 180 degrees about the origin and you end up with the same function. Sine of x or sine of t is an odd function, okay? If it's an even function, it means if you take a line around the y-axis and you reflect it around the y-axis, you end up with the same thing. Cosine of t is a even function. Now, if you've got an even function, you have only cosine terms in the solution. Okay, so only an will have a value. If you've got an odd function, okay, you only have bn terms. Okay, an terms are 0. Okay, and if you want to wonder why, chapter 9 of your notes, I think it's chapter 9 or 10, no, I think it's 9, is an appendix, okay, in which I've got the maths behind Fourier series. So if you need to revise your Fourier series knowledge, okay, just to understand where we're going, then refer to chapter 9. But in there I talk about odd and even functions. But it's quite clear, if you follow the notes there, you'll see why an terms are 0 if you've got an even function. Sorry, an terms are 0 if you've got an odd function, and bn terms are 0 if you've got an even function. This is an odd function, so we know that an is 0, and the bn coefficients we can calculate, okay? So on odd times an odd will mean that you can multiply the integral by 2 and take it from 0 as opposed to from minus t0. So that's where that equation comes from. f0 is a constant, so that can just come out, okay? So I end up with 2f0. And obviously, I take the integral of sine n pi t upon t0. You get cosine, minus cosine out here. And obviously, depending on what the n value is, you're going to get a value or you're going to get 0. Because obviously, if n is such that cosine n pi is plus 1, you get 1 minus 1, which is 0, okay? And the only case that happens is you end up with, if n is even. If n is odd, okay, then you get a 1 minus minus 1, so that becomes 2. So 2 times 2 is 4 over n pi. Okay, so that's where that comes from. And so our forcing function can be written as a sum. Okay, 4f0 upon pi, which is a constant, so it's outside the term, there's no n in here, and then we've got sine n omega t divided by n, okay, where n is odd. Now it's useful at this stage to replace n omega with omega n, okay, it doesn't really matter, but obviously n is going to be an integer from 1 to 1, it's 135 in this case, it's just odd, but so obviously we have omega 1, omega 3 and omega 5, okay, it doesn't really matter, they are the same thing. okay, when you're referring to the third harmonic, that's 3 times the fundamental harmonic, okay, which is omega 3, or 3 times omega. And so we can write it like this, okay, so we've replaced n omega with omega n, and there's the sum from n equals 1 to infinity when n is odd only, okay, so when n is even, we don't worry about it. That's the sum when n is odd only. So, each term in the Fourier series is a sine term. You must solve the equation of motion to find the steady state response x of n for the nth harmonic input. Okay, and the nth harmonic input, f of n, we know is bn sine of omega nt. Okay, so if we go back to our equation, okay, this is essentially b of n, okay, which is upon, so for f naught upon n times pi is b of n sine of omega nt. Okay. So for the nth term, so if I take f equals 5, then obviously I've got b5, okay, sine of omega 5 times by t. But I'm solving it, like I said, in terms of arbitrary n. And it's quite clear that if we go back to chapter 3 and we can see quite clearly that this is a sinusoidal forcing function, so we have to try the sinusoidal trial function, which we saw in the previous lectures. Okay, and in your tutorial, where alpha and beta are constants that we've got to determine. And so if you go through the motions, differentiating the trial function twice to get x double dot, okay, and then we plug it into our forcing function, so mx double dot plus kx, so here's our mx double dot plus kx, equals that nth passes of force. So by comparing coefficients, okay, of cosine omega t and n omega t, then that term must be 0. Okay, so it's quite clear that alpha is 0. And this term, it can't be 0, it's equal to b of n, so beta must be b of n divided by k minus m omega n squared. So like I said, mx double dot, here's our mx double dot, okay? On this line, I've rearranged mx double dot to put it in terms of cosine omega nt and sine omega nt. Okay? Now obviously on the right-hand side, there's no cosine term, so this bit must equal 0. And on this side, okay, there is a sine term, so this bit here must equal b of n. And if you solve for beta and alpha, you get alpha is 0, and beta is b of n divided by k minus m omega n squared. So the steady state solution for that nth term is b of n divided by k minus m omega n squared times by sine n of t, okay? Because that's what we solved for. We solved for x of n. For a particular value of n, okay, like I said, we try the trial function here, okay, differentiating this term here. We differentiated twice to get x double dot. We plug it into our equation, mx double dot plus kx equals the force, okay, and every force, the nth force is going to be bn sine of omega nt. Okay, you solve for alpha and beta, and then you plug in beta, and you get, for the nth harmonic, okay, then my nth response is going to look like this. And obviously the solution is the sum of all those responses. Okay, so I take the sum of those x of n terms, and I get x of t. And if I plug in x of n, which is what I had, is this term over here. Now bn, we know what bn is, because we've worked it out. And so you can plug in the value for bn and you end up getting this as our solution. Okay. So, to summarise the steps. Step 1, we've got the Fourier series. Okay. And that's what we worked out the Fourier series to be. So f of t, like I said, is the sum of these terms. So obviously b1 sine omega 1t plus b3 sine omega 3t and b5 sine omega 5t and so on. Okay. Ad infinitum. Now for each one of these terms, we've got to find x of 1, x of 3, x of 5 and so on, okay, based upon this. So what we're going to actually do is we're going to find x of n, okay, because it's going to be the same process for all of those terms. And where b of n we know is for f naught upon n pi. Okay, that's what we found out what bn of n is. When n is odd. When n is even, b of n is 0. So we don't consider the 0 terms. We just the even terms. We just look at the odd terms. So when n is odd, b of n is 4 f naught upon n pi. Okay, that's what we found. So what you do in the second step, you solve the differential equation, which looks like this. Okay, we solve the second order differential equation of motion with the trial function that matched the forcing function. Okay, and resulted in that. Okay, where we found beta was this b of n upon k m minus m omega n squared term. And so if we took the first, third, and fifth harmonics, obviously x of 1, you stick in 1 wherever you see an n, and you end up with this term. Okay, and obviously b1 we know is at 4f0 upon pi. Okay, x of 3, obviously stick 3 where you see an n, 3, 3, and 3, and then we have 4f0 upon 3 pi times by that function. And so on, fifth term, seventh term, and so on. And then what you do, to get them, you add them all up together. So you x1 plus x3 plus x5, and so you end up looking in longhand like this, okay? So those are those three terms just added together. The common feature was this bit. The bit that changed was the bit in the brackets. And obviously we can write this as a sum, which is where that comes from.